Alright, so we have already done some questions on homogeneity. Now we move on and we'll do some questions on SI base units. So the first question says derive SI base unit of force. And we already know that force has the formula F is equals to ma. Solving for this formula, the unit of mass is kg, unit of acceleration is meter per second squared, so the unit of force comes up to be kg meter per second squared. The next part says a spherical ball of radius r experiences a resistive force F due to the air as it moves with speed v. So radius r experiencing force F due to air moving with speed v, and this resistive force is given by the formula CRV. We need to find the constant C, the units of constant C. So C is equals to F upon RV. We'll make C the subject, so we can find its units. We know the unit of force is kg meter per second square, so we'll put them as it is. We know that the unit for R is meter, and we know that the unit for V is meter per second. Hence, simplifying it, m goes with m, and it's kg s minus 2 upon ms minus 1. Simplifying it further, it becomes kg s minus 1 m minus 1. So the base unit of the constant C is kg s minus 1 m minus 1. The second question is June 2011, paper 2-2, question 2a. The question says a sphere of radius r is moving in a fluid with speed v. There's a frictional force F acting on the sphere, which is given by this expression. D depends on fluid. We need to show that the SI base units of D is kg m minus 1 s minus 1. So in order to find the units for D, first of all we need to know that since 6 pi is a constant and we have to find the base units, so we'll ignore the constants whenever we are working on base units. We'll make D the subject, F is drv, so that means D would be F over rv, where F is the force, R is the radius, V is the speed. So we'll plug in the units. Unit of force is kg m s minus 2, like we did in the first question. Then R is the radius, so its unit is meters, and V is speed, it's ms minus 1. Simplifying this, we'll get kg m s minus 2 m2 s minus 1, right? So this m is squared. Now simplifying it further, we'd get kg m into m minus 2 and then s minus 2 s1. So m and m minus 2 will become m minus 1 kg m minus 1, and then simplifying it further, it would be kg m minus 1, s minus 2, and s1 also becomes s minus 1. Hence it's proved kg m minus 1 s minus 1 is the SI base unit of D. The third question is June 2012, paper 2-1, question 1a and b. A1 says state the SI base unit of volume. We know that volume is what? L cubed, right? So its unit would be meter cubed. And then show SI base unit of pressure is kg m minus 1 s minus 2. So pressure is what? Pressure is force upon area, and force is kg m s minus 2, while area is meter square, so it becomes kg m minus 1 s minus 2, right? M2 goes up there, it becomes m minus 2, so m and m minus 2 will become m minus 1. Hence proved that as well. Then B says that the volume V of the liquid flows through a pipe in time t and is given by the equation volume upon time is equals to pi PR power 4 HCl. P is the pressure difference between ends of the pipe of radius r and length L. The constant C depends on the frictional effects of the liquid. Determine the base unit of C. So we need to find the base unit of C. Again, we'll do what? We'll make C the subject. So as we move on, the first thing that we'll do, we'll ignore these constants, because whenever working with base units, SI base units, we ignore these. So that means my C would become P R power 4 upon L into T upon V, right? And hence, if I need to find the units of C, it would be kg m minus 1 s minus 2 for power, for pressure, that I have already worked out there. For r, its radius, so its unit is meter, r power 4, so meter power 4. And then you see that it's time, so the unit for time is seconds, length in meters, and v, it's the volume, it's in meter cube. Don't confuse this with speed. So working all this out, m3 below and m will get cancelled with m power 4 up there, so my unit would become kg m minus 1 s minus 1. Now is the fourth question, June 14, paper 2 question 1. And question says, show that the SI base units of power are kg m2 s minus 3. So we know that power is work done upon time, and work done is what? Force into distance upon time. So force into distance upon time, and we know the unit of force is what? Kg m s minus 2. Unit of distance is what? Meters. Unit of time is what? Seconds. So m and m becomes squared, s goes up there, s minus 2, s minus 1, it becomes s minus 3. So finally my equation for power is kg m2 s minus 3, which is proved, right? Then it says that the rate of flow of thermal energy is given energy Q upon T. Rate of flow of thermal energy Q upon T in a material is given by the equation CAT upon X. A is the cross-sectional area, T is the temperature, X is the thickness, and C is a constant. We need to find the SI base units of C. So that means we'll make C the subject once again. And when we make C the subject, so what would be next? It would be Q upon T, which is basically power. And then power is equals to CAT. We need to find the units of CAT. And CAT will become C is equals to P into X upon AT, P into X upon AT, right? So I say power, or I say energy upon time, or work done upon time, it means the same thing. Now the unit of power, as I have proved up there, is what? Is kg m2 s minus 2. God forbid if I was not able to prove this, I could have used this equation, these units directly up over here. So power is kg m2 s minus 3. Over here x is what? X is the thickness, it's measured in meters. And then you have A is the cross-sectional area, again meter square. And what is next? It's T. T is the temperature, which we measure in kelvins, right? So if we simplify this, m2 is there, m2 is here, we get those two cancelled, and hence we get the equation kg s minus 3 m kelvins. Kg s minus 3 m kelvins. So far we have been working on questions in which we would find the base units of some constant or base unit of some physical quantity. But now we are going to see that there are some constants, some quantities which would have no units at all. So the question is from June 2013, paper 2 question 1b, and it says that the power available from the wind is given by this equation, which is CL square rho V cubed. L is the length of each blade, P rho is the density, V is the speed, and C is the constant. So we need to show that C has no units. In order to do that, what we'll do first, we'll make C the subject. So this equations come up to be C is equals to P power upon L length squared into density into speed cubed. So we know the units of power, it's force into distance upon time, so the unit of power would be kg m2 s minus 3. Kg m2 s minus 3, this is the unit of power, so we place it here. And then we have L as in meters, so L square would be meter squared, hence we keep the unit of L. We keep the unit of L over here as meter square. And then we have speed, which is cubed, and the speed has the SI base unit ms minus 1, so it would be m3 s minus 3. So speed is m3 s minus 3. And then we have rho, the density, which is mass upon volume, and hence its unit is kg per meter cubed. So density, its unit is kg per meter cubed. Simplifying that, we'll cancel kg with kg, then we'll cancel s minus 3 with s minus 3, and then finally we'll cancel m2 up there with m2 below here, and then we'll cancel m minus 3 and m3, and hence we'll end up having no units for C. So this is the next question in series of no units. The question says that the intensity of a progressive wave is defined as the average power transmitted through a surface per unit area. Show that the SI base unit of intensity is kg s minus 3. Now we need to show the unit of intensity. We know this is from 2015 paper 23 question 1, and we know that the intensity is power upon area and power is work done upon time. So power is equals to kg m2 s minus 3. We have worked this unit many times now. And intensity is what? Intensity is power upon area, so it's kg m2 s minus 3 upon area, that is meter squared. Simplifying that will result in kg s minus 3. Hence we have proved this. Now the next part says that the intensity I of a sound wave is related to the amplitude x naught. The wave I is equals to k rho c f squared x naught squared. So rho is the density, c is the speed, f is the frequency, and k is a constant. We need to show that k has no units. So in order to do that, what we'll do, we need to first know all the units. Density is kgm minus 3, c is the speed, so it's ms minus 1, f is the frequency, so f squared is s minus 2 because frequency has unit s minus 1, and x naught, which is the amplitude, so its unit is meter, so x naught squared has the unit meter squared. Now plugging that into the equation, it would be I upon density into c into f squared into x naught. Intensity is what we have just proved, it's kg s minus 3, and density, it's kg m minus 3. And then we have speed, it's ms minus 1. Then we have frequency, which is s minus 2, and then we have amplitude, which is x naught, hence it's m squared. So kg gets cancelled with kg, s minus 3 with s minus 3, this s minus 1, s minus 2 will become s minus 3. So this gets cancelled with this s minus 3, and then you have this m and m2. So hence we'll cancel that out as well, and finally we are left with no units. Here's the next question from November 2014, paper 2-1, question 1. B. The question says mass is made to oscillate vertically. The time period t of the oscillation, the time period is t. The period t is given by t is equals to c under root m upon k. C is a constant, k is the spring constant. We need to show that c has no units. So again we'll make c the subject, and we know that k is what? K is the spring constant, so its formula is what? Its formula is force upon area. We need to know its unit as well, force. Then over here t is equals to what? T is equals to c m power half upon k power half, because under root is power of half, and then we'd end up t into k power half into m upon m power half is equals to c. So we know that the unit for t is the time period, so the unit for t is seconds. Then k power half, k is what? K is the spring constant, and we need to find its unit. So over here it's the formula for spring constant, which is f over e. Hence I'll simplify that, and f is kg ms minus 2 and e is m, so m gets cancelled. That means the unit of k spring constant is kg s minus 2. Kgs minus 2, this m shouldn't be there, kgs minus 2, just remove this m, right? So yes, all right, so that's the unit of spring constant. Now kgs minus 2, so I'll just save that for now, and that would become kg s minus 2 power half, because it's spring constant power half. Spring constant is kg s minus 2, so kg s minus 2 power half. that all in bracket, and then its mass power half, so its unit is kg power half. Simplifying it further, it would become s into kg power half. When I open the bracket, it would be kg power half, and then s minus 2 will be multiplied with 1 upon 2, and that would result in 2 and 2 getting cancelled. That will become s minus 1. Simplifying it further, we would know that this same unit would be copied as it is over there. So you can see this kg power half and kg power half eventually gets cancelled, right? Kg power half and kg, sorry for that. Now this s minus 1 is there, so kg power half gets cancelled, s minus 1 and s gets cancelled, and hence I have 1 as the unit of this. So this marks the end of base units, and in our next topic we are going to be moving on to studying uncertainties.